very pleased to introduce Professor Taki Sulenidis from Chicago University. And here we have the title of his talk, The Status of the Theory of Stochastic Viscosity Solutions and Fully Nonlinear First and Second Order Stochastic PDEs.
But there is no green.
Okay. No, but
Yeah, I
pretend it's on. I assume one is green, is it?
or red. Okay, it's on. All right. All right, so thank you very much for showing up and for the invitation from the organizers of this workshop. I feel that I feel obligated, he's not here, but you know, I think as one of the organizers, I feel I have to thank Zlatan for all the work he did. I think without him, there was not going to be a meeting. So anyway, so I waited for the title to the last minute because I was debating between talking either about stochastic PDEs, which is a general program, or about random homogenization, but then I saw Peter has given a number of talks about this topic, so I thought it is best to present you a survey of what is known and how far we have gone in this theory with Lyons. So far, it's half the book is written, so I brought it here just in case anybody has a question. Okay, so so I started, I guess, what time, so I know till when I'm going. 5 to 5. Okay, so I shouldn't delay very much. Okay, so and I want to apologize for my handwritten Beamer presentation, but this was going to take me a month to do it, so I thought it was easier to do it by hand by making a lot of copies. Okay, so these are the type of equations I want to consider. So they are fully nonlinear and this object. Now, does anybody see this thing? Okay, so they are fully nonlinear second order. F is degenerate elliptic. And here I have a nonlinear term that depends on the gradient, u in principle, and some, call it b there for Brownian motion or whatever it is, as long as you can make sense out of this expression. We would like to do it in a bounded domain with boundary conditions. Of course, we don't know how to do anything about boundary conditions, so everything I'm going to describe is going to be in Rn, Rd, and the kind of solutions I will be considering will be pathwise, so almost surely in omega there will be bounded uniformly continuous functions in Rd cross 0t, and basically we want H to be some vector in Rm and B some path in Rm. Okay, so that's the theory, and the kind of results we have. There's one more that you will see later on. Basically, we will have the following two cases. Either we're going to have just U dependence separated plus something that involves gradient dependence, or we're going to have just gradient. Okay, so what I mean is we're going to have the dependence on U, and as far as dependence on the gradient, it will be either x dependent, but only one Brownian motion, let's call it Brownian motion, or there will be as many arbitrary Brownian motions, but no x dependence. And one of the big open problems is how to handle the case where there is h depends at the same time, so it's not separated this way. H depends both on the gradient and u, and I will try to explain why that's a problem. We have some special cases, but I doubt that there is a general theory that allows for dependence on the gradient and the u multiplied by the same noise. Okay, so someone may ask why the heck anybody wants to study this problem, especially in the nonlinear setting. And by the way, I'm not doing white noise in space. The best we can hope to do is color noise. It's the problem is nonlinear, and nobody knows how to integrate by parts in X. I mean, the whole point of the theory is that there are no solutions in the sense of distributions and so on. So white noise in space is beyond that. So the reason we became motivated to study this problem, it was an old paper by Funaki, where he was studying another model, which you will see next. But the whole idea was how to describe an interface that moves by some prescribed normal velocity, part of which is white noise. And people like that, especially in the physics literature, because they hope that such kind of things, not this one, it will give a model for nucleations, the cases where you have a front popping out of nowhere. So if somehow you decide to study, let's say, a motion of an interface by mean curvature plus some white noise term, and you use the level set approach, that immediately leads to the following fully it's a quasi-linear there, but it's fully nonlinear in terms of the noise term. So it leads to this stochastic PDE for which there was no theory. So one of the motivations to do all the stuff we did was to be able to study such kind of equations. And therefore gives sense to the following problem, which is related to what Funaki was interested in. So you go back to this very nice reaction diffusion equation. W is the double well potential with wells, let's say, at -1 and 1. And let's say you perturb that. What you do is you perturb the zeros, this -1 and 1, by epsilon times some nice function there, and the B epsilon is some kind of regular approximation to Brownian motion. Then one can prove, using the theory I'm going to describe, that as epsilon goes to 0, indeed you see an interface, the solution goes to 1, -1, and you are separated by an interface moving by curvature plus white noise. And this was actually, as a problem, was the first problem, the first theorem that made the, not theorem, the first case where people, and that's when I say people, I mean Ota and Kawasaki many years ago, in a formal paper. This was the first paper that made the prediction the Allen-Kahn equation was related to motion by mean curvature. And of course they have formal computations which I have never been able to understand, with this thing being actually Brownian motion. One of the byproducts of what we have done is that this cannot be true. So if you put here, really Brownian motion, so if you look at the stochastic PDE semi-linear with additive Brownian motion, then it is not true that you can have this thing at the limit, because the Brownian motion creates a lot of instability, so you're not going to go to 1 and -1 in that case. However, if you allow for a regular approximation of Brownian motion, so regular means think of a convolution with a power of epsilon where the power is not, okay, this I always get mixed up. Either it cannot be too large or too small, one or the other. Then one can prove this kind of result. Okay, so let's keep going. Another application of the theory was this work we had with Yip. So let me try to explain actually the second part of the, okay. So if you know anything about motion by mean curvature, you have seen this pathological example where you have a figure 8, so two balls touching, and you let them move by mean curvature, and I'm using metaphysical terms. The mean curvature doesn't think, but if you are at that point, mean curvature doesn't know whether it should go this way or out or in. And so what is known for the mean curvature motion is that basically there is a whole family of interfaces. There is a minimal and a maximal, and the reason is that somehow at that point either you decide you are two circles that are touching, in which case you detach and you keep moving, and these are the inside, or you decide that you are basically something that came from the outside and you just stopped at that point, so you remember that you came from the outside and you open up. Okay, so that's the classical result about mean curvature. So the question is, what happens if you introduce some noise here? And so in the case you have mean curvature plus epsilon Brownian motion, this result is for Brownian motion, then what happens is instantaneously you open up. And you have an interface like that, and even when you let epsilon go to 0, you converge to this, which is nothing else but the maximal solution for motion by mean curvature. So if you put a white noise there, the white noise is so strong that forces you to open up, and then you converge to the maximal solution. So that's a kind of stochastic selection principle. An interesting problem is to see, okay, if you are not touching really, but how far away can you be before you see the same phenomena? So if there was a distance epsilon to some, you know, I'm colorblind and I can never see this stupid thing unless I have to put it somewhere else. And anyway, so if you put some distance there, whether you're going to have a similar, pointer, I have the same problem. I look like a Greek ancient, it will look like the movie, the Thermopylae, so I don't want to do that. I was thinking of you standing like that, so I said, you know, it's, the only thing I need is a sword, and then we will be fine. In case there are any hostile questions. So, Nikolai, when you are ready for your question, let me remember to get my spear there. Anyway, so that's a problem. And the last application I want to mention is stochastic scalar conservation laws. I wrote it here, so I'm sorry that this is part of my Beamer thing that is sometimes the copier doesn't do the right thing. So you can have, this is written in a very complicated way. So this is like a multi-D conservation law, but scalar, the classical one, and it's perturbed either by white noise multiplying the derivatives or by white noise multiplying just the solution. We're going to hear a talk, I guess, on Thursday about the second case. So the semilinear result, so take A0, F0, it's something that has been done by Debus and Vauvel, and we have done with Pertam and Lyons, we have done the case where the noise multiplies the derivative. And you're going to see from what the way I'm going to describe things that the method we have developed allows you to deal with this issue with derivatives. So, okay. All right, so the meaning of dot there, I guess I have to go a little bit fast here. So if we are in the case where we are really dealing with Brownian motion, then basically the dot means Stratonovich, and I just wrote down the expression that what do I mean? I wrote down the formal expression. Of course, we never look at this problem. We don't know how to deal with such a thing, and I have two motivations why it's Stratonovich. One, of course, is the usual thing you're going to have from ODEs. You approximate an ODE with, I mean, I wrote as a PDE, but this is the classical example that B epsilon is smooth approximation. You will go to Stratonovich. Another way to convince yourself it has to be Stratonovich is to go back to the mean curvature equation I said, and I used the word level sets, and level sets means that basically means that if U is a solution, phi of U has to be a solution if phi is non-decreasing. And the only way this can happen is if you put Stratanovich there, otherwise it's not going to work. Okay. All right, now previous work, I start writing down some references for the linear, quasi-linear case, and I quickly realized I'm going to get in trouble. So I put at least all the names of the people who may be present and have worked on that. If I miss someone, I apologize. I promise to add it. So there is an extensive theory in the uniformly elliptic case for linear or quasi-linear problems, but the key word there is uniformly elliptic, linear, quasi-linear. So in some sense, you have some regularity, and one can take it from there. And the only nonlinear work I knew before, and actually I didn't know, someone pointed out to me after we had done after we started working on that. So the only nonlinear case is the work of Kunita, who has a short time theory for stochastic Hamilton-Jacobi equations. Short time because it has to do with characteristics. So what Kunita does is basically, it doesn't write it like that, but take this stochastic Hamilton-Jacobi equation, and then you write down the characteristics, what they should be if everything was nice. Suppose you know what the formally you write down the characteristics for this Hamilton-Jacobi equation. And then what Kunita proved is that, of course, introduce a stochastic flow. There are a lot of interesting things there. So these are the characteristics that will correspond to that equation. H is smooth. And then Kunita proved that omega by omega, there is a time for which you can invert the x characteristic. And all of us remember from our first year PDE class that if you have in that invertibility, you have a local in time smooth solution for the Hamilton-Jacobi equation. And the key thing again is local in time. All right. So as long as everything is smooth, that's the solution. And he defined the flow and all that stuff. Okay, and this is something, I mean, as I said, it's not hard. If you are not interested in deep probabilistic questions about measurability, this is not a hard thing to do. If you want to worry about measurability and selection principles, then you have to look at Kunita. Okay, So now that's where Beamer becomes a mess. So let's go like that. All right, so what is difficult about doing the nonlinear problem? I already mentioned that in the linear or quasi-linear case, uniform ellipticity was saving you. I'm interested, let's forget about that. Let's just concentrate on the stochastic Hamilton-Jacobi equation, but let's say that for some reason you want to have a long time existence. All the applications I mentioned to you were long time examples. We never cared about finite, for small time, because the small time also depends on the regularity on the initial data and so on. All right, so what are the issues? If you want to go for nonlinear theory, of course, there is no point-wise solution. There is no regularity. We know that even if there was no noise. And there is no, when I say no martingale theory, there is not a theorem, but we didn't see how to do a martingale theory. Well, that's very much related to having a solution in loss. And let me just explain heuristically here why it's hard to expect to have a solution in law here. So I wrote down, this is stochastic DE, and we know that if we want to study the stochastic DE, it's enough to know its equivalent, martingale or whatever, to know the behavior of the solution of the PDE that corresponds to that generator for L initial data. And that's the basic thing that goes behind martingales or solutions in law. So let me write now the analog for stochastic PDE. If this is the stochastic PDE somehow we want to study, then if everything were smooth, the infinite dimensional PDE that would correspond to that the same way that this corresponds to this is this equation here, where now the variables, of course, are functions. It's phi, and this will be a second order operator, and this is a second order operator in an infinite dimensional space, and no matter what base you use, this is going to be unbounded, and there is no theory that can cover these things. I'm not saying it cannot be done, but there is no theory that can deal with such kind of problems. So this idea of doing solution in law goes away, and then we are stuck with the problem the way it is. Okay, and the last one I want to show you is the fact that the trivial thing that you may say in the case that you had one Brownian motion only, and that will work if you were in the case of stochastic D, is changing some time, changing the time. So this is only if there was one Brownian motion. So one can attempt to say that u of xt is some universal function u with a change time b of t, where the u solves some autonomous Hamilton-Jacobi equation. And of course, there you have a problem, because actually what's happening here, you have shocks. So you start having shocks, the solution oscillates because of the presence of the b of t there, and you have to go forward, backward in shocks, and there is a problem. And just to convince you this is not the case, I want to write down two examples, and it's amazing how much one forgets if you have all these notes. I thought that we only had the first example, but yesterday reviewing my notes, I realized we have another one that is more dramatic. So the first example, we knew it some time ago, and actually appears also in the paper of Funaki. It says if you try to solve this Hamilton-Jacobi equation with initial data just the length, this is related to the geometric motion I was describing before, then the solution is like that. So it is, I'm not going to read it, you see. So this would be the solution if we could make the change of variables, but there is some extra thing that builds up because of the oscillation of the Brownian motion. I think this must be negative there, but anyway. All right, so that's one example. And now here's another one that is, because here you may argue that, okay, this is not a smooth function, so there may be a problem. So here is as nice as you would like. This conal type stochastic solution in 1D. Let's assume we have a periodic initial data, and I write you down what will be the solution up to the first time that the difference between the maximum and the minimum of the Brownian paths becomes 1 or larger. And then, of course, one can, so this is the random time here. So up to that time, this is the soup, this is the inf of the Brownian motion. Up to the first time that this distance becomes bigger than 1, the oscillation becomes 1. That's the formula for the solution, and there is a theorem here that this is indeed the formula for the solution. And after that time, there is even more complicated. I don't think there is any educational value of writing down, apart from the fact that it looks complicated. All right, and it is. All right, so now having said all that stuff, let me start preparing you about what we want to do. So this is a fully nonlinear, forget the H, that is the theory of viscosity solution. So it's, what did I do here? I don't want to do that. Did I say that again? Ah, yeah. Okay, so I mentioned, so what we'd like to do is like to use viscosity solutions. Viscosity solutions is the way to study these fully nonlinear equations, the F part of the equation. So remember, my problem had a D and F with a lot of stuff there and an H. So viscosity solutions work perfectly for that, so maybe they can work for this. Viscosity solutions are, for those who don't know, is like distributions, but for fully nonlinear second-order problems. They are the thing that allows you to replace the solution by smooth functions in some sense, and it's a point-wise theory because you just evaluate at places where you can touch your solution from above and below by quadratics. And then you have to be able to write the equation there. So there is no, here because of the dB, there is no point-wise formulation, there is not enough regularity to do anything. And let me explain to you the issue of the regularity. So what I'm writing down here is when B is smooth. So one formulation of the viscosity solution is to say that U is a subsolution to this equation if the following happens. If you look at the propagation of the maximum of the solution is minus a smooth function, so that maximum of uxt minus f of x, phi of x, then this as a derivative has to be less equal h, the Hamiltonian, evaluated with the derivative at a place where the maximum is achieved, times b prime. That's equivalent to the viscosity definition. And then, of course, it's infimum over all the points x bar that you can do that. So I said if this is smooth, this is the case, then we know that at least for the Brownian case, there's no things are simple here. Somehow that will automatically go to Stratanovich. So you may expect that at the end, the correct definition is this. That the correct definition is that the maximum of u minus phi should be less equal that quantity, but now Stratanovich there. And the problem is that there is not enough regularity in the x bar. The x bar is just the place where the maximum is achieved at time t, and there is not enough regularity available to make sense out of this integral in the Stratanovich sense. So you are doomed that way, although this looked the most promising. And of course, you cannot, you say, okay, you are in trouble there because you insist on Stratanovich, but Ito's differential will fail completely because with Ito's differential, one of the key things of the theory is that the maximum of two subsolution is a subsolution. There is a maximum principle involved, while here, if you just use Ito's differential, it's not hard to prove that the Ito's differential over the maximum goes the wrong way. All right, so that won't work. So you need to do something else. And to do something else, I want to revisit the linear theory, and because that was our original motivation. That's how we came up with the approach I'm going to say. I'm going to go back to the linear theory and redo a piece of the linear. When I say linear, I mean linear dependence on the noise. I keep saying noise here, but this can be, I mean, can be rough paths if you like to call them rough paths, as long as something happens later on. So that's the linear problem. Fully nonlinear there. So even that, as I'm stating down, is new in the sense that was not done before. And this was our canonical example, so we never really even claimed that as a theorem because we thought that was step one, step zero. Okay, so what did we do here? I mean, this is, everybody has done this in this talk, so I'm not claiming that we are rediscovering anything here in the linear case, but the most naive way, and I'm not a probabilist, so we were very naive when we started that, it was to say, okay, let's find a way to eliminate the random part from the equation. And the best way to eliminate a random part from the equation in the linear case is, of course, to realize that you can change variables, you can change unknown, and absorb this part and that part into the f. And this is nice here, works perfectly well because everything is linear. So if I write down, going back to the characteristics, if I write down the characteristics that correspond to this stochastic part, and I wrote them there, these are linear things. There is nothing to, you learn quickly. By the way, the invertibility of the characteristics has to do with the x characteristics. So the x characteristics here solve an autonomous, or not autonomous, they solve, are decoupled from the rest of the system. So because of uniqueness, this x is always invertible globally in time. And therefore, if I define, make the new unknown to be u of xt to be some function v evaluated at the inverse of the characteristics, is not hard to, it's a straightforward computation. It takes a lot of derivatives, is to prove that actually the v solves this random. There is an omega floating around there, if I'm in the case of the Brownian motion, but there is no noise anymore. This is a classical Hamilton-Jacobi equation with a little bit messed up coefficients, but that's what it is. So as long as you have, so now let me make a comment here. if you look at the system, wherever the system is, there you see it. I mean, it's not worth. If you look at that system, whether I use Brownian motion here, I use rough paths or whatever, anything that allows you to make sense out of that and get a C2 solution. So whatever theory you want, whatever assumptions you want to make, as long as you have a C2 solution to that system, which is a linear system of stochastic, linear in X, when I say linear, it's a system of whatever it is, then under those assumptions you can always reduce this problem to that. Of course, I said I need to assume enough to be able to have nice solutions for that. And I'm not going to be careful at this level what are the assumptions. But the key thing I wanted to say is no matter what notion of paths you want to use for the B, if you have a linear problem, linear combination of things depending on the gradient and you can invert globally the characteristics and convert the problem to this, and then standard viscosity theory tells you that this problem has a unique solution. You pull it back and you are in the previous situation. So, and as this is what I said, Brownian motion irrelevant. The only thing you need to do is to solve the system of characteristics. Okay, so once we realized that, we decided that the solution, the way to solve this problem is to try to do that in the nonlinear case. And but before I do that, let me explain why it works. So what happens is the characteristics follow, again, go back and remember your elementary PDE class. The characteristics, the way the characteristics are defined is that you know along the characteristics you can carry information about the gradient of the solution and the solution itself. That's what characteristics do for Hamilton-Jacobi equations. The noise here is irrelevant. Okay, and why does it work in this particular case, although I had du and u dependence, is that basically in the linear case the separated dependence on du and u decouples their behavior. And let me explain what I mean by that. So if I write down the characteristics, if I write down the Hamilton-Jacobi case, the characteristics of this general problem, you see there is a very heavy coupling is going on in the x characteristic. But if you are in the linear case, if the Hamiltonian was like that, then you see the x characteristic does not see the u. And that allows you to decouple the problem. In other words, for those of you who have thought a little bit about that, when you do conservation laws, what the characteristics do is propagate the value of the solution. When you do Hamilton-Jacobi equations, the characteristics propagate the value of the gradient. So if you try to do the general problem with gradient and u dependence, you run into a trouble, which you don't have it when the problem is deterministic, because when it's deterministic, you just take differences, absolute values, and you do it. But if it's stochastic, you cannot do that. Okay, so that's the reason this separated behavior works here. All right, now this is a tutorial, so I assume it doesn't count towards my time. So what is the idea about viscosity solutions? So the idea about viscosity solutions is to use test functions to go around the fact that there is a lack of regularity. And the second big secret about viscosity solutions is that you can adjust your test functions to the particular equation you have, as long as you can prove some kind, as long as you are consistent with the whole theory. So if you can make a theory, if you decide to use chairs as test functions, it's okay, as long as you can prove uniqueness, as long as you can prove that if you put an epsilon in front of the chairs and you let the epsilon go to 0, what you get is consistent with the previous theory. So you are free in the theory of viscosity solutions to build your test functions, as long as for these test functions you can go and do the original problem too. All right, and otherwise the definition, which I'm not going to use it very much, says that something is a subsolution, that anytime you can compare it, actually it's worth saying that. So something is a subsolution if and only when the following thing happens. You take a smooth function of space and a smooth function of time. You look at the possible maximum of u minus phi minus g, if there is one, local maximum. If there isn't, you don't do anything. And then you can replace at that point all the derivatives by the derivatives of phi and g. All right, so that's the whole thing about the theory. And so remember that. Now, okay, so let me now, what I want to do is I want to combine the two ideas I show you so far, namely the definition of the notion of the viscosity solution and the transformation I had before to eliminate the stochastic term. All right, I want to eliminate the stochastic term, but I want to do it in the context of viscosity solution. And what will be the difficulty there? The difficulty will be, let me write it here, and again, let's stick on the Hamilton-Jacobi case. So you cannot do anymore a global change of variables. The problem is nonlinear. So what you're hoping to do is to do it at the level of the characteristic of the test function. So you solve this problem with the idea is build test functions which at the level of the test functions you can eliminate the stochastic part. Now the problem you're going to have, of course, is because the problem is nonlinear and this is my test function, I cannot have global in time solutions. And so what I'm doing is, in principle, and that's only for those who know a little bit about viscous solutions, one of the beauty of the theory of viscous solutions is you can use very simple test functions. In particular, quadratic functions are the ideal test functions. You can do amazing things in viscosity theory just using x squared for test function. The problem is, and it's free, you can do whatever you want with that. The problem is that when you go to the stochastic case, you don't have any more this freedom. Your test functions have to be robust. The test functions have to be the propagation by that equation of x squared. And that kills you. It kills you because all the things you are doing with your eyes closed, if you have been working on this subject for some time, you cannot do them anymore. You cannot take differences, you cannot multiply them, you cannot expand them. I mean, you have to deal with these local time smooth solutions. All right, so these are the kinds of problems we can investigate. So notice what I have. Semi-linear case, arbitrary many Brownian B's with linear first-order dependence. That's the extension of the linear case. Or so far, although now I think we know finally how to do multi-Brownian motions, we can do du dependence with many Brownian motions coupled with u dependence as long as these two things are independent. And as I said, there are serious difficulties if you insist in doing the same du and u. But one case, for example, we know how to do is if H is positively homogeneous of degree 1 in du, then we can do it in that case. But anyway, that's... all right, so now let me revisit quickly the semi-linear theory. I'm running out of... I'm afraid... okay, so... the game is at 7:30, so we have time. All right, so semi-linear case, I'm writing it up there. This is classical. We just did it because it came across, and you do changing here. This problem is global. The only thing you do is you make this change of variables. You find the function phi, which solves. Okay, I'm getting time to get the weapon. All right, so I'm just doing what I described there. Now, the only thing is that the H is very simple. This is nothing else, but after the fact we learned was the Dawes-Sussman transformation. Then you make a global change of variables here, like that, and then, as I showed in the linear case, everything drops out, and now you have a new equation which depends on omega, and the new Hamiltonian looks like that. Dots mean derivatives of phi with respect to the initial data. So assumptions, whatever you need to assume on H in order to have C2 solutions for phi, actually C3 will be even better, and whatever you want to assume on B in order to have C2, C3 solutions. So Brownian motion if you want to assume rough paths, whatever, that's independent as long as you have a C3 solution of this problem with respect to V. This is the transformed equation. Now you need to study this problem and figure out that you have a good theory, and it turns out that it required a structural condition on the original F. So the original F has to have this property. This is derivative with respect to the second derivative. This is derivative with respect to first derivative, derivative with respect to u. That combination has to be bounded either from above or below. Notice that if the problem is linear, of course, these things are satisfied. The only thing you need there is that. So it extends the linear case, but introduces a structural condition, and we don't know what to do without the structural condition, because if you are brave enough and you go back and you write the characteristic equations, I mean, there is a way to see that that condition is meaningful, even if you use characteristics. Okay, so that extends to, as I said, to the, problems like that very easily. The only thing you need is, as I mentioned, the solvability of that problem. Okay, so that takes care of the case where you have semi-linear dependence. I will call that semi-linear dependence. You should be able to make automatically that transformation anytime the problem is semi-linear and get rid of that. Incidentally, why did I say if I have joint dependence if I had joint dependence on gradient and u, is because notice this term, if the problem is positively homogeneous, I can get rid of it. So anyway, let's not worry about that. Now let's go to the fully nonlinear case. And I write down, so here we have to work now differently. Now I have to do this inversion I talked about there. So I want to write viscosity solutions. So here's the point. I take any smooth function phi. This is like the regular case. I take any smooth function of time, g, and I look at I look at the small time evolution of the test function phi given that semigroup. Again, whatever the notion of path you have doesn't matter as long as I have smooth solutions there. I look at this expression. Notice that if I had viscosity solutions, the classical ones, I don't put there that, I just put phi, but here I have to put a small time evolution to that. Then if it just happened to have a maximum at that point, I can go back to the equation and a miracle happens, all the stochastic part goes away. And I have an equation at that point, and then it took us about 7 years to realize that actually with this definition we could prove uniqueness. But now there's a theorem that says that viscosity solutions defined in that sense are unique, exist, they're stable, and all that stuff. And of course, there are more things afterwards we don't know that we know. And once more, it will extend in the case where I had the separated dependence there. Okay. So that's with this. So I don't know. I mean, maybe I should spend a little bit of time here. Notice that all the difficulty is the fact that, as I mentioned earlier, your test functions now are very robust. So you have to be able to deal with things that are short-time smooth solutions of the nonlinear Hamilton-Jacobi equation. So making estimates with them are not so simple anymore. Okay, so now what are the kinds of results we can prove? I will present two classes, H smooth and H not smooth. And I want to stay a little bit also in the non-smooth case because one of the applications I mentioned at the beginning was motional, and there it was du. H was du, and H with du will never be able to find the local time smooth solution, length of du. All right, so if I take H that is independent of X, we can do arbitrary continuous paths, and the result is if you assume H is C2, there is a unique stochastic viscosity solutions, comparison stability, and so on. So arbitrary continuous path, HC2, you do that. This doesn't cover the example I had, the du dB, but that will be the next transparency. And the second result, which as I said now, I think that we are able to do multi-Brownian motions at this point. We can do X dependence with many Brownian motions, but now the assumptions are horrendous. So I write down here two classes of assumptions, and I will explain why you need these assumptions. So if one class of assumptions, this one extends the linear case. So if I want to do a nonlinear problem that resembles the linear one, I have to make all these crazy assumptions to control up to third derivatives. I mean, right now you think I went mad. I didn't. At least I don't know that yet. So you can think about it. Anyway, so I will explain the last transparency, how such kind of conditions come in. But they are related to the fact that I want to control the interval of existence of the test functions. Okay, and the other assumption, class of assumptions, extends the separated quadratic case. This is a little bit more palatable. So you see there is a decay, there is a growth and a decay on the gradient vector for the Hamiltonian. All right. And in the non-smooth case, because remember I have to cover that. Now, the definition, of course, cannot be the same because in the non-smooth case, I'm not going to be able to write the characteristics. But what happens there is there is an intriguing connection between the regularity of the path and the regularity of the H. So in particular, if we insist on having arbitrary continuous paths, we can go down to H's that are difference of two convex functions. And this is sharp. You cannot have a good theory if you go below the class of functions which are difference of two convex functions. So if you want to have a theory that says you can work for all arbitrary continuous paths, H has to be like that. Here we are lucky because that's a convex function. So it works for mean curvature, no problem. And then there is some kind of relationship. If you take paths that are alpha Hölder continuous, then some elementary interpolation will tell you that actually the h has to be, in the usual sense here, the h has to be Hölder continuous, the appropriate derivative of h of that type. We cannot go down to that. We can only do it for this plus epsilon. So, but you see, there is a very intriguing connection there. So you're going to ask me, how do we do this? We cannot do characteristics. So here we did we studied with great detail the following issue. So think about what's happening in this problem. Forget the x, so we don't worry about that. So what you have is you have cancellations. The thing goes up, comes down. This was also the reason that in these formulas I saw you, there were these messy parts, the maximum and the minimum. So the solution goes up, comes back, goes up in time. Time goes up, comes down, because time is like b. So what you do is anytime you go back, go up and down, you go through the shocks. So something is going to happen. But there is still some cancellation. And so we have a very explicit estimate about how the solution behaves in terms of the cancellations of b. So we can see the max and the mean popping out. I didn't want to write it because it's going to take me half the transparency. But once you have that, you see immediately that, first of all, is sharp, because in these two formulas I wrote down completely matches what you get. And it also tells you that there is no hope to do, I mean, it is what it is. Now, if you put x dependence in this, it doesn't work like that. I mean, we cannot do it for x dependence. So here we need to do something different. And then we need to have very careful estimates about how you, if you solve the problem for smooth h, the error you make if you assume that h has the right Hölder continuity, so you can define things and so on. Okay, I'm even surprised I'm going to finish this thing. Okay, so there's a lot of mess here that I thought that I was going to go slower and therefore I wouldn't be able to do it. All right, now I want to show you the why we get all this crazy dependence and why the x-dependent case is hard. I have 5 minutes, huh? Yeah. Okay, good. All right, so to do that, I have to explain to you the idea of the proof of uniqueness for the viscous solutions deterministic case. There is no other way to do that. All right, so this is a crash. So you either give me an extra minute or I charge you for this. I mean, it's all right, so let me put at least everything there so you can see what happens. Okay, so how do you do? I charge because it's free tutorial. I mean, you know, it's, let me say I want to prove uniqueness, deterministic things here, Hamilton-Jacobi equations. I have a sub-solution, I have a super solution, and I have some relationship on h that we're not going to go through that. So if u and v were differentiable, how would you prove uniqueness for the solution of this problem? You look at u of u minus v minus, you introduce something in time just to minus alpha t, and then you say, okay, if this expression had an interior maximum, you have a contradiction, because at the interior maximum, ut will be equal to vt plus alpha, and du will be equal to dv. You plug them there, and you get a contradiction because alpha is positive. That's the classical maximum principle proof. And then that implies that alpha has to be less equal 0, and if alpha is less equal 0, if alpha is positive, the maximum happens at t equals 0. Everybody knows how to do that. I mean, it's a triviality. Okay, but now I want to deal with viscous solutions. I don't have maxima. Even if I had some, I don't know whether they will happen. I'm sorry, I know I have maximum points. I don't know whether I have derivatives. And even if I had derivatives, I don't know whether they will be at the maximum. So what you do is you play a trick and you double the variables. So now you decouple the x and the y. It's not anymore u of xt minus v of xt. It's u of xt minus v of yt. Of course, you want to be a little bit careful how you decouple it, because you introduce a penalization that as this parameter lambda goes to infinity, of course, you recover the original maximum. Now, this function, it looks perfect for the Hamilton-Jacobi equation, because I have u minus something smooth, and I have v plus something smooth. So now, if I had a maximum, I can apply the definition of the theory, all right? This thing, okay, I have to make some assumptions at infinity. So for the purpose of this transparency, assume everything is periodic, so that maxima are achieved, and I don't have to worry about things being at infinity. So it's a simple thing to check because of continuity, that as lambda goes to infinity, this has to go to 0, and a maximum of that goes to a maximum of this. Because if x and y don't go to 0, this is going to blow up and everything is bounded, okay? And also, since everything is periodic, this function is going to have a maximum. Assume the maximum is at t positive, then you are in the perfect situation. Freeze y, then u of xt minus lambda x minus y is frozen. Square minus alpha t has a maximum, so you get an inequality from there. Then freeze x, then v plus lambda x minus y square x frozen has a minimum. You write these things in the definition of the viscous solution. A miracle happens that x derivative of x minus y squared is minus the y derivative of x minus y squared. This is an amazing miracle that happens in this case, which allows you to conclude that the two h's are the same, modulo the fact that they have different x's. So let me say this in a little bit more sophisticated way. It's easy to see that because of what I just said there, the doubled function solves the doubled equation. So I just subtracted the two equations, and I'm just saying the difference solves this problem. Now you see why you conclude, because if you didn't have the, I'm sorry, this is y here. And all right, so that's the essence of the theory. So let me review them and put them together in the next transparency. And now you have here the whole theory. Okay. These are my assumptions. This is the doubling. I just convince you that that solves the doubled equation. And therefore, because I'm at the maximum, if you go a little bit below in time, at time t bar minus h, my doubled thing, the double function, is below lambda x minus y squared plus the value at the maximum. So now the only thing I'm doing is, if I could build a smooth super solution to that problem, I'm done. Because in the deterministic case, it's true even in the stochastic case, by definition, subsolutions are below smooth solutions or smooth super solutions. All right, that's part of the definition. So if I had a smooth super solution, and this function actually is indeed a smooth super solution of the doubled equation, then this will be below that. Then you do the calculus you have, you realize that something happens, and you come down to this expression. H is how far you went back in time. This is the error between the lambda x minus y squared and the smooth super solution. And you notice that as h goes to 0, that goes to 0. So if you divide by h, you get 0, while on the other hand, you had alpha positive, which is the same contradiction as if everything were smooth. And this is the proof for the Hamilton-Jacobi case. The second order case is more complicated. But the Hamilton-Jacobi case, you see, it's very simple. I write down the double equation. I build an explicit super solution, smooth, and I can compare it immediately. And as long as I have done it with the right size of things, I have the uniqueness. Now, the key thing here is I built a smooth super solution. And if you remember, at the definition I gave for a solution, I don't know what is a super. I know how to define a smooth super solution, but I will always have, if I'm lucky, I will have smooth solutions. So if I were to repeat this program in the random case, and that's the end. So so now I go to the same problem, but I put a stochastic term there. So I write the difference. No difficulty, this is true. The difference is also a stochastic solution of the difference of the doubled equation. These are continuous functions, so I can play the same game, subtract something, and I'm exactly at what I had before. All right, now this is the place where before I said, okay, I can build a smooth super solution based on lambda x minus y squared. Just I wrote down something that involved x minus y squared. I cannot do that anymore. What I have to do is I have to solve this double Hamilton-Jacobi, stochastic Hamilton-Jacobi equation with this initial data. Now this is, I have to solve it, exactly, all right? And I have to solve it hoping, I went back h, I want to choose the h so that the interval of existence of that problem is long enough of smooth solutions that I can start at h and at t bar minus h and go up to t bar. Now, that's an issue because the interval of existence depends, think deterministic Hamilton-Jacobi equations, it depends on the Hessian of the initial data. The Hessian of the initial data is lambda. Lambda goes to infinity. The interval of existence is like 1 over the Hessian. So as I want something here to be able to control the interval of existence in terms of lambda, but cannot go to 0 very fast because I will have a problem. All right, so but let's say somehow I can do it. So I repeat what I did before. Everything boils down to this computation. So the difference of the smooth solution that starts there minus his initial data going at time, this has to be, this is like t minus h here. So the interval is h, has to be like that. So now I have to be able to repeat, as I said, something is missing here. This is a smooth solution for interval h. So I have the difference of the smooth solution of the Hamilton-Jacobi equation minus the initial data. I run it for time h, and I want to know that this difference is little of 1 in terms of h. And I want to be able to do that. Remember, the only parameter I have here is lambda. Lambda goes to infinity. So I need a very detailed estimate. There's no doubt that that goes to 0 as h goes to 0, but it has to go like little 1 of 1. So I need a very detailed estimate on the interval of existence of solutions to the double equation in terms of the Hessian of the initial data, the lambda. And that's a pain. And if you want to do it in general, of course, you don't have this issue in the case where there is no x dependence, because there the solutions are, they don't have, the real difficulty is when there is x. And this is the reason I had all these crazy assumptions on h. Now, I think we figured out a way to go around that, but what was entitled in this problem is we had to control the interval for how long the Jacobian of the x characteristic stays non-zero. And that's not a simple thing to control. And in doing that, we had to do all that mess. And so that's where the assumptions come, and this is how this thing works. I'm done in the transparency. So if you are interested, infinitely many open problems from numerical schemes. I mean, we heard a beautiful talk, the first talk of the conference, about how to do numerical schemes. Now here, the problem is fully nonlinear, it's more complicated. Remember, I built an omega by omega solution. It's a pathwise solution. This construction gives you no information about the stochastic behavior of the solution. And we have some very preliminary results in one dimension for certain equations where we saw that all things can happen. But maybe there is an invariant measure as t goes to infinity. Who knows? Maybe there is something there. Numerical results, boundary value, boundary conditions, which of course is a very interesting problem. And I don't know. I think I mentioned all of them. All right, or there are more, but I forget them. All right, so I stop. Thank you.
Thank you very much for this interesting talk. It's time for comments and questions.
I carry this thing for nothing, my weapon.
Yeah, please.
So in the case where you have just h of du, so
Yeah.
u in x, so there you can have your driving path, the b, can have more than one component, or you can have arbitrarily low alpha holder characters.
Yeah, as long as the h is the one that adapts to the. So as I said, it can go up to continuous paths, but then I have to have h to be the difference of two convex functions. It's false below.
But how comes you don't? I mean, how comes you can go all the way down to continuous path?
Because if there is x independence, the characteristics are just straight lines. So in the x independent case, let's think one path. The characteristics are just straight lines. So it's a completely pathwise solution. It's the same way that when you do the rough paths, the only reason you do them is if you have x dependence. If you don't have, so that's why you can do it. So it's a pathwise theory. You can do it. The stochastic conservation law is exactly the same way. We just do it at the level of, it's again kinetic formulation. You just invert the characteristics. It's the same thing. There's nothing more there. What is difficult is to what was the real difficulty we had with that is we had to reprogram ourselves to do proofs about viscous solutions without knowing this big freedom you have when you can use x minus y squared. And believe me, it's very hard to learn it from the beginning. And once we figured out how to do it, then, here's a thing we don't know how to prove. Hamilton-Jacobi case, h smooth whatever, domain of dependence. There has to be a domain of dependence for this problem. I mean, after all, if there is no noise, there is a domain of dependence. But we don't know how to prove that. Because if you remember, the proof of a domain of dependence for Hamilton-Jacobi equation is based on the fact that you can build a very explicit super solution that in the right cone is a super solution equation. We don't know how to build super solutions. So such a simple question, we don't know how to do.
Thank you.